along, and if you'd like to share screen and go, that'd be great. Thanks very much.
Thank you so much. So I am Haripriya, and thank you for the introduction. I'm doing my PhD at the University of Adelaide, so joint PhD between Melbourne and Adelaide, and I am about to complete my first year. And I work in complex analysis. And the talk that I'm giving today is based on some of the work that I did in my MPhil, which I completed the start of last year, first half of last year. Okay, so I'm just going to share screen because I have slides. Okay, perfect. Oh, I need to move the bases. Okay, so I hope everyone can see this. So my aim is for this talk to resemble a journey through, is it? Okay, here we go. Can everyone see the slides? Yeah, perfect. Okay, so my aim is for this talk to resemble a journey through the rich history of the so-called H principle. And that's a pivotal theory that's focused on homotopical methods for solving partial differential relations. My talk is, of course, going to have a special emphasis on the manifestation of the H principle in complex analysis. And this is really for my own selfish reasons, because that's the area that I work in and that I love. And a lot of this mathematics, as I said, was the basis of my MPhil. But the complex analytic side of it is also the lesser known side. And it's wonderfully elegant in the way complex analysis tends to be, and real analysis sadly often fails to be. So the story, it really starts all the way back in the 1930s with this classical theorem of Whitney and Graustein. Okay. It states that immersions of the circle into the plane R2 up to homotopy through immersions are characterized completely by the winding numbers of their tangential maps or their velocity maps. So I'll put this up precisely. Okay, precisely any two immersions from the circle into the plane R2. These so-called immersions are maps whose derivative is nowhere zero, okay, are regularly homotopic, meaning homotopic through immersions, if and only if their velocity maps, which are loops in the punctured plane, have the same winding number. Now, what does this mean exactly? So it is a fundamental result in algebraic topology that loops in the punctured plane are uniquely classified up to homotopy by the number of times they wind around the puncture, right? So in other words, homotopy classes of loops in the punctured plane are in bijection with the integers. That's what I've got up here. Now, what the Whitney-Graustein theorem tells us is that regular homotopy classes of immersions themselves from the circle into the plane are in bijection with the integers. And this is where everything started. We can actually say so much more. The Whitney-Graustein theorem was the first incidence, as far as I know, and as far as my supervisors know, of this notion called the H principle, or the homotopy principle. This derivative map from the space of C1 immersions, I'm not sure if I do this, like, I'm not sure if you can see the cursor. Anyway, this derivative map from the space of C1 immersions to the space of continuous loops in the punctured plane, Whitney and Graustein said that this just induces a bijection of path components. But actually, it's a weak homotopy equivalence. So really, it induces a bijection of all homotopy groups, the fundamental group and all higher homotopy groups. So loosely speaking, this space and this space, the space of immersions and the space of loops in the punctured plane, they have the same rough shape. Now, we now bring ourselves to the latter half of the 20th century, right at the heart of the 1980s. So we're going to have to turn back through time a little bit when we start to talk about the complex analytic analog. But first, let's meet Gromov's H principle. Now, to any differential relation R, We may associate a unique algebraic relation by treating the derivatives as new independent variables. So what do I mean by that? For example, consider a loop f in R2, parameterized by t, say. We could have a differential relation that says df dt is never zero. Df dt is not equal to zero. Df dt is never zero. And the associated algebraic relation would be a is not equal to zero. So we're just replacing df dt by this new variable a. It's an algebraic relation. A solution to the algebraic relation is called a formal solution. Now we want to try to deform a formal solution into a genuine solution continuously, perhaps smoothly, depending on what kind of problem we're working with. We have different regularities, but we want to try to deform in a regular way a formal solution into a genuine solution of this differential relation. The basic H principle is said to hold if any formal solution can be deformed through formal solutions into a genuine solution of the differential relation. Now we're going to equip the set of formal solutions of R, the differential relation, and the set of genuine solutions of R with the appropriate function space topology. And we will denote the space of genuine solutions of R by SR, standing for solutions, S, and gamma R is just the set of formal solutions, algebraic solutions to the algebraic relation. Okay. And the parametric H principle, we will say that that holds for this differential relation if this inclusion, the inclusion that goes from genuine solutions to formal solutions, if that is a weak homotopy equivalence, meaning if these two spaces have the same rough shape, loosely speaking, we'll say that the parametric H principle holds. Okay. So now we have this H principle that I've been hyping up a little bit. This is the one-dimensional H principle for ample differential relations. It's a particular form of it. It's a classical form. It's an important one, and it was probably the one that Gromov first worked on and in detail. Of course, when I say in detail, if you have a look at his monograph, it's very hard to make sense of it because everything made sense to Gromov, but he leaves a lot of the details out because it was in his head and maybe he thought it was obvious. It really isn't. But we'll talk about this a little bit. I'm not going to go into the proof because the proof goes on for many, many pages, but I'll talk a little bit about how we prove it as well. Okay, so let E from E to S1, just let that be the trivial bundle, okay? And let R in E be an open and ample differential relation. I'll explain what that means in a second. It's a differential relation that sits inside the bundle E. Okay, then this map that goes from solutions to genuine solutions to formal solutions, right? It's just given by differentiation, is a weak homotopy equivalence. Now, what does it mean for a differential relation to be ample? We say that it's ample if RP for every single P in the circle, this thing RP, if that's ample. And we say RP is ample if for every point A in RP, the interior of the convex hull of the connected component which contains that point is all of Rn, the affine space Rn. I hope that's okay. Now, why is this useful? Well, we see immediately that the strong version of the Whitney-Graustein theorem is actually just a special case, a very, very special case of Gromov's H principle for ample differential relations. The differential relation is just R2, removed R2 with the point 0 removed. So, and this is, it falls out immediately. That's what that is. Yeah, which is what I've got up here. It's an easy application. We just set RP to be R2 with the origin removed. How do we prove this? It's a tedious proof, and it employs a particular advanced technique called convex integration theory, which was invented by Gromov in the 1980s as well. Now, this intricate method was developed by him to prove the H principle for ample differential relations. It was literally invented to prove this. But it's an important technique in differential geometry and in complex geometry today. The Convex Integration Theory Bible today is a book by David Spring called Convex Integration Theory. Now, it's an amazing book because he leaves out absolutely no detail, which is what Gromov failed to do. But it's also the worst book to learn from because his treatment is unbelievably technical and not even slightly intuitive. But I'll make a few remarks. So given a first order differential relation, I, which is just the interval 0 to 1, into Rn, it can be useful to relax the relation a little bit and consider the convex hull of the original relation. That's the idea behind convex integration theory. And we iteratively apply something called a convex integration process to a given formal solution. What we want to do, as I said in the H principle, is to deform a formal solution into a genuine solution. We start by relaxing the differential relation, consider the whole of the convex hull, and then apply the convex integration process. What's that? Convex integration process, every convex integration process, it generates a map, which is defined as an integral formula whose integrand is a family of loops sitting inside the proper differential relation. And if this sounds a bit cryptic, just bear with me for a second. The last thing I'm going to say about convex integration theory is this. So this is called the Fundamental Lemma. This is a key stepping stone in the process of, it's a key stepping stone in the proof of the H principle for ample differential relations. So I'm just going to, so let P be a compact Hausdorff space. In our case, it's a circle, but it's obviously more general, so I just put this up. E is the trivial bundle, and R is an open subset. So this is our differential relation, such that for all P in P, Rp is a non-empty open subset of Rn. Okay, let sigma just be a section of this differential relation, which means that, it's a section, but its image sits inside the differential relation. That's what that means. And that is also how we denote formal solutions. Okay, and Z is just any old section, but it has to satisfy this relation. So at every single point, it will sit inside the interior of the convex hull of the corresponding point sigma P. And this is for all P in P. Then there exists something called a C structure or a contractible structure over P with respect to Z sigma, which satisfies this integral. So what's a C structure? A C structure, as I said, it's a contractible family of loops, which sits inside the differential relation, has base point sigma, and it strictly surrounds Z. So we'll have such a family, and that family will satisfy this integral. And this, if you sit over this for a few days, for me, it took some weeks when I was doing my master's, this is what leads to the proof. It's a really important part of the proof of Gromov's H principle for ample differential relations. But that proof does go on for many pages. And actually, I wanted to say, if you would like to pore over the details of it, you are welcome to have a look at chapter 3 of my master's thesis. But if you're feeling brave, please have a look at Spring's book. But like I said, it's far from intuitive. But there is another very good source, which is something that I use to learn from. It's Vincent Burley's lecture notes, which are not published, but you can find them on the internet, on convex integration theory. And it has some really nice, helpful pictures as well to help elucidate some of Spring's very, very, very technical, dry approach. Okay, so now we go on to some of the parts that I really like. The first evidence of the H principle. So it's very natural to consider how it manifests itself in complex analysis because of the concurrent developments in complex geometry in the 20th century. So if you're wondering when the H principle, or maybe you're not wondering, but if you're wondering when the H principle first appeared in complex analysis, it wasn't very long after Whitney and Graustein's theorem. In fact, it was just 2 years after. It was in a theorem of Kiyoshi-Oka of 1939. So Oka proved, and this is in modern terms, that a holomorphic line bundle on a Stein manifold is holomorphically trivial if it's just topologically trivial. In fact, if you have a holomorphic line bundle which is topologically trivial, any continuous trivialization can be continuously deformed into a holomorphic trivialization. And there is another form. Now we're going back to the second half of the 20th century. Another form of the holomorphic H principle was due to Gunning and Narasimhan. And now this is a seminal theorem. Some of you may know about this. This is the one that I'm going to be more interested in this talk because it's nice to go through the proof of this one. Here it is. So we let X be an open Riemann surface, so a non-compact Riemann surface, and theta, a non-vanishing holomorphic one form on X. Now, I'm sure everyone knows what that is, but if you don't, just know that it's a device for fitting a notion of differentiation on manifolds, and you can just treat it as a symbol if you want. But what it really is a section of the holomorphic cotangent bundle. Sorry, yeah. Okay. So given a holomorphic map F from X into the punctured complex plane, C removes the origin, there exists a holomorphic immersion, capital F, from X into C, and that just means that dF is nowhere zero, okay? So there exists a holomorphic immersion, capital F, from X into C, such that little f can be deformed into dF on theta through non-vanishing holomorphic functions on M. Now, dF on theta is, of course, a genuine non-vanishing holomorphic function in itself. And as you can see in the form that it's in here, this is a H principle. We're deforming a formal solution into a genuine solution. And in fact, it's as you can see, it's an analog. It's a holomorphic analog of the Whitney-Graustein theorem. And it's on Riemann surfaces as well. The proof is, of course, nowhere near as messy. In fact, the proof, it's actually a very elegant proof that can be done Gunning and Narasimhan did it in just 4 pages. How did they prove it? Well, this is the statement that they actually proved, and it's not very hard to show that it's equivalent to what we saw before. Let X be an open Riemann surface, and let theta be a non-vanishing holomorphic one form on X. Then there exists a holomorphic function G from X into C, such that the non-vanishing one form e to the G theta is exact. So they're giving a precise homotopy. They're actually giving a homotopy between the two. So what does it mean for this to be exact? Well, that just means that there is an immersion capital F such that dF is equal to e to the G theta. Okay, the proof uses basic homology theory and Riemann surface theory, and I'm going to try and give you a sketch of the proof. Okay, let D prime be open subsets of X, which are connected, relatively compact, and Runge. Runge means that the complement does not have any connected components. Okay, so there are no holes. Now, assume that the boundary, there are no compact holes. Okay. Now, assume that the boundaries of D and D prime are smooth and that the closure of D sits inside D prime. Then there exists a basis for the relative homology group H1 D prime D that can be represented by simple piecewise differentiable loops gamma 1 through to gamma p in D prime. Now, I'm going to try to explain this proof intuitively. But before I begin, okay, there is a well-known topological classification that every compact orientable surface with boundary is homeomorphic to a sphere with a finite number of handles attached and open disks removed, right? So in particular, in this case, any connected component of the closure of D prime remove D is homeomorphic to such a space, a sphere with handles attached and disks removed. So let's start by looking at it this way. We can identify this homology group, this topological group H1 D prime D, with the abelianization of this fundamental group. And this is just a standard result from algebraic topology, elementary algebraic topology, of course. Now let W mu, I should have picked better symbols for this because when I'm saying it out, it's so clunky. All right, let W mu be a connected component of the closure of D prime, remove D. All right, now on each handle of W mu, just choose a canonical pair of simple loops that are not null homotopic and not homotopic to each other. Does that make sense? So we've got a handle. One of these loops goes around this way and the other loop goes this way. Oh, this way. The handle, a loop that goes this way and a loop that goes this way. Okay. Then for each deleted disk lambda, whose boundary is disjoint from the boundary of D prime, which, D prime is the little set that sits inside it, choose a loop which forms a boundary of a slightly larger disk in D prime containing lambda. Okay, so for each deleted disk, sorry about that. So for each deleted disk lambda, whose boundary is disjoint from the set that sits inside the big set, so the little set. So we just choose a loop that forms a boundary of a slightly larger disk, which contains lambda, okay? And for the remaining disks, we just choose simple arcs that join one to another, and then take these arcs to be disjoint from each other, and then extend these arcs through D to form simple loops. If you sit over this for a little bit, since we're looking at it as an abelianization of the fundamental group, it's very clear that this is what we have to do, because this is an exhaustive list, in fact, and we might be doubling up a little bit. And we just extract a basis from this set. This is a finite set, and it generates it. It's exhaustive, so we can just extract a basis from that. Then this is what Gunning and Narasimhan did. Okay. So let D and D prime be connected. So let D prime be connected, relatively compact Runge subsets of X which have smooth boundaries. And D prime sits inside D, just the same setup as before. Now we take a non-vanishing holomorphic one form omega on X, and we assume that it's exact, okay, inside D. So so if you have any piecewise differentiable loop in D, and you integrate over it, then it has to be 0. And this also means that you can find an immersion such that df is equal to this. These are equivalent conditions. Then, given any epsilon, there exists a holomorphic function f on X, such that if you have omega e to the f and you integrate over that, over any piecewise differentiable loop in the bigger set D prime, then the integral will be 0, and you can control the size of f as well. And this is the key stepping stone, actually. After this, we use induction. So I'm just going to go through an outline of the proof. So it is a known fact that the topological groups, all of these topological groups have the homotopy type of a bouquet of circles. That means that this exact homology sequence is of this form. It cuts off, and this is how small it is. And moreover, this exact sequence, it splits, as these homology groups are all free abelian. And so we can apply this lemma, and the previous lemma, this one. We can apply this one to each of these pairs. So D prime D, the relative homology group associated with this pair, and the relative homology group associated with D and the empty set. And you can get loops. So gamma 1 through to gamma p for this pair, and gamma p plus 1 through to gamma q for this pair. Then all of these loops together, they represent generators for this topological group H1 D prime, and that's because the exact sequence splits, right? Now let lambda I so this is a bit, let lambda I be the image of gamma I in D prime. So take continuous complex valued functions U1 through to UQ on this image, on the union of this image. They have disjoint supports, and we assume that UI, each of these UIs, is 0 on the closure of D for 1 through to P. So I think it's obvious why we can do this, because so for 1 through to P, that's they form a basis for the relative homology group H1 D prime D. So you can definitely just assume that all of the UIs are 0 on the closure of D. And of course, if it forms the basis for D, then the homology group H1D, then where are we? Then UI is 0. Oh, yeah, okay. That's for the second half of this. For the first half of this is what we assume, and we also just assume that UI is 0 on any of the gamma J's, on any of the other loops, if I is not equal to J. And we require it to satisfy these two integral conditions. So for I from 1 through to Q, we can construct holomorphic functions Fi, which approximate these functions which just sit in gamma 1 union through to gamma Q. We can construct holomorphic functions on all of the entire Riemann surface, which approximate these arbitrarily closely on this. And for that, we use the Magellan-Bishop theorem. Now, of course, its application is not entirely direct. One of the cases we have to use the Magellan-Bishop theorem twice, but it's not particularly difficult to see how to use it. Then finally, we just let A be, 1, 1, 1, 1, 1 for the first P coordinates, and then 0 for the rest of the coordinates for P plus 1 through to Q. Now, assuming that these approximations, these holomorphic approximations Fj are good enough, then if you were given a delta, we can find a point X, which is within delta of A, such that this integral is satisfied, which means that the integrand is exact. Now, why can we do this? It actually just comes from Hurwitz's theorem, from elementary complex analysis. And there we are, we're almost there. Well, actually, that proves that lemma, but this is just for a compact subset, of course. And then we do the obvious thing of proceeding by induction. We're going to fix an exhaustion of the entire Riemann surface by relatively compact Runge subsets, and we can always do this. And we just do this over and over and over. And that's enough because we know we can control the size of F. So that way we get a function exactly as we wanted. That's exact. We get a differential one form like that, and then we're done. So that's the Gunning-Narasimhan theorem. Now, I'm going to say a few words about what I did in my MPhil. So I worked out a parametric H principle for holomorphic immersions of open Riemann surfaces into the complex plane. So the Gunning-Narasimhan theorem, that was a basic H principle. Essentially, I worked on parametrizing that, extending that to all of the higher homotopy groups, the fundamental group, and then the higher homotopy groups. So basically, this fits naturally into two contexts. So you can view that as a holomorphic analog of the strong Whitney-Graustein theorem, or you can view it as a parametrization, as I said, of the Gunning-Narasimhan theorem, which is the basic H principle for holomorphic immersions of open Riemann surfaces. So this is what I did. So if we let I from X to C be the topological space of holomorphic immersions from X into C, equipped with the compact open topology, and then we let O from X into C star be the space of holomorphic functions just from X into C star, also with the compact open topology, we showed, or I showed, that these two spaces have the same rough shape. They have the same weak homotopy type. So if we choose a non-vanishing holomorphic one form, theta on X, which we can always do, then this continuous map, which we get by taking df, we take f and send it to df on theta, which is of course a genuine non-vanishing holomorphic function. That map is actually a weak homotopy equivalence. So these two spaces have roughly the same shape. Oh, I don't want, okay. So a few words on this. This is actually a special case of a stronger result by my supervisor, Finnur Lárusson, and his collaborator, Forsternič. This is from 2016. Now, they sketched a proof by invoking some advanced results, but there was no direct self-contained proof of this very interesting case at all. It sort of fell out as a consequence of a very different result. And it was sort of mentioned, like, oh, here is a remark. This is quite interesting, but there was no proof of it. And yeah, so what I did was, I worked out a detailed self-contained proof of this. I'm not going to go into that proof because that proof just ran for so many pages. But it is obviously a geometrically interesting special case. Now, why is it interesting? Okay, so this parametric H principle, it allows us, as I said, to understand the rough shape of the space of immersions through algebraic topology alone. Because the target space is easily seen to have the weak homotopy type of the space of non-vanishing continuous maps from X to C star. In particular, the path components of the space of immersions, right? They're now in bijection with ZR, where R is the rank of H, the first homology group of X with integer coefficients. How does one prove this? Okay, a few techniques: convex integration theory, Morse theory, and this other advanced tool called period dominating sprays. Now, I say it's an advanced tool, but it manifests itself quite transparently in this situation. And actually, I would like to talk a little bit about period dominating sprays very, very briefly. So if we let X be an open Riemann surface and we let M be a compact submanifold in it with boundary, and we take a holomorphic immersion on the compact submanifold M, again, have a nowhere vanishing holomorphic one form theta on X. And then on M, the compact submanifold, if we have a function M into C star, so nowhere vanishing, that's given by, df is equal to little f theta. And we have, of course, we can choose simple piecewise smooth loops that form a basis of this first homology group just on this compact submanifold. Then there exists a way of controlling the periods. So there exists a holomorphic map like this, such that, so our map F, it sprays out a bunch of other maps continuously or smoothly, however you want it to be. It sprays out other maps. The period map, meaning, well, if you take the if you integrate over each of these smooth loops, the values you get, if you integrate the f or anything else really over that, whatever value you get, of course, if you get 0, that means it's exact. That period map actually has full rank. So this is a way we can control the periods, because what we do is it's an iterative process. We try to fill out the Riemann surface gradually. So we pause, this is where we use Morse theory. We pause every time there's a change in the homotopy type, and we adjust the map using period dominating sprays. So we approximate, and then we find something close enough so that the period can be adjusted and the map remains exact. that's basically how it's done. And yeah, that's how I would like to conclude. If you're interested in some of the references that I was talking about, Spring or Borelli, that's up there. And yeah, thank you so much for listening. I'm sorry about those interruptions. That threw me off a little bit, but thank you. I think I'll stop screen sharing now.
Great, thanks so much, Haripriya. That was fantastic. Can you guys hear me better now? I changed my mic. Okay, yeah, it might have been just a poor setting. Okay, well, great. That's fantastic. Thanks so much. Do we have any questions? I have a question. So you talked about how you sort of proved this, gave an independent proof of this generalization in your master's. So can you tell us a little bit about what you're doing now?
Okay. What I'm doing now is completely different to that. I'm basically looking at applying, so the Oka principle is basically, well, it's the H principle, essentially. You can look at it as the H principle in complex geometry in a way, on Riemann surfaces or on Stein manifolds. And I'm looking at how it sits in K-theory. So it's pretty, I'm not going to say interdisciplinary, it's in pure maths, but it's into area. And I'm a year in, so it'll be a while before I can find the right words to explain what I'm doing. But yeah, it's still the H principle, but I'm looking to forge a connection to K theory. So yeah.
Cool, sounds interesting. Thanks. Any other questions? Okay, well, if there are no other questions, let's thank the speaker again.